we mentioned that we can consider I as a set of all items in a store, so item 1, item 2, all the way to item M. The store has M items, and then we have a database transaction or a transaction database T, which has all the transactions T1, T2, all the way to Tn. N transactions we have in the database, where every Ti of these has one or more items from I. So every Ti has one or more items of I, and every transaction in the dataset is given a transaction ID TID. The Apriori algorithm. It's used to mine item sets from transactional databases for Boolean association rules. Remember, Boolean association rules, we'll come to that in the next video. Now, we have a concept here that we need to remember. This algorithm is based on the idea that a subset of a frequent item set must also be a frequent item set. A frequent item set, any subset of it must also be a frequent item set. We'll come to that when we give an example, but just remember this. For example, if we have an item set which has two items, item 1 and item 2, and it's a frequent item set, then the subset of item 1 and the subset of item 2, both of them are considered frequent item sets. It's an iterative approach, so it runs through several iterations to find frequent item sets, and it uses the frequent item sets to generate association rules. So what it does is it uses a level-wise search where we have k item sets, lists of k item sets, and we use them to explore item sets of larger size, larger by 1, so k plus 1 item sets. Always larger by 1, we increase the size by 1 of each of item sets. In this algorithm, the frequent subsets are extended one item at a time. This step is known as candidate generation process. Then groups of candidates are tested against the data. We'll come to what that means in the example. It identifies the frequent individual items in the database and extends them to larger and larger item sets as long as those item sets appear sufficiently often in the database. So we extend them by 1. We extend every step by 1. We'll come to that in the example as we mentioned. And the Apriori algorithm determines frequent item sets that can be used to determine association rules. So we need to extract the frequent item sets first, and then they can be used to determine association rules. Now, from Professor Said's material, this algorithm takes advantage of the fact that any subset of a frequent item set is also a frequent item set. We mentioned that, and we're just repeating it to keep remembering it in the algorithm. The algorithm can therefore reduce the number of candidates being considered by only exploring the item sets whose support count is greater than the minimum support count. Now, for the support count, we spoke about it in the last video. We can use it as a fraction. We can have a minimum support count as a fraction between 0 and 1. And then what we do is we divide the frequency of items by the size of the transaction database. We divide by n. If we use the minimum support count as an integer number, then we only compare it against the frequency of items rather than the frequency divided by the size of the transaction database. All infrequent item sets can be pruned. So we have a concept of pruning here. We'll come to what it means in the example. So the infrequent item sets, we prune them if they have an infrequent subset. So when we do the subset idea, this idea here, if any of these subsets is infrequent, then that should also be considered infrequent. As I said, the example will make things much clearer. So again, just in plain English, how do we do it? We build a candidate list of k item sets. A k item set, by the way, is an item set that has k items. So we build a candidate list, and then we extract a frequent list. We need to be building two lists at every iteration. Now, for the frequent list, I'll be using fi as a frequent item set, for just as an abbreviation. In textbooks, sometimes you find L rather than F. It's just the same thing. After that, we use the frequent list of k item sets after we extract the frequent list to determine the candidate and frequent lists of k plus 1. As we mentioned, we increase the size always by 1 at each iteration, and then we use pruning in the middle of this idea of step of determining the candidate and frequent list of size k plus 1 from frequent list of size k. we keep repeating until we end up with either an empty candidate list or a frequent list. If one of them is empty, then we stop there. That's the stopping condition for the algorithm, and then we return the frequent list of k minus 1, because our current list can be empty, so we return the frequent list from the previous iteration. Enough talking, I know, too much text. Let's have a look at an example for things to make sense. Let's assume that we have a transaction database that has 5 transactions. The size is 5. In the first transaction, that's transaction ID, we have 3 items, 1, 3, 4. Second transaction, 2, 3, 5. And as you can see, these are the items in each transaction. In the first step, we build a list of item sets of size 1. So k here is 1. And we have 5 items, 1, 2, 3, 4, 5, as you can see, and we count them in the transaction database. How many times do they appear? 1 appears 3 times, 2 appears 3 times, and so on and so forth. And then let's assume that our minimum support count equals 2. Then we need to remove any item sets with a support count less than that. Notice, not less than or equal, less than that. That's why for item 4, for that item set which has the item number 4, that's red, because 1 is less than the minimum support count, so we remove it, and that's our frequent item set from the first iteration. It only has 1, 2, 3, 5 with their support count. So that's the very first step, the first iteration. It's nice and easy. In the second iteration, we extend now this frequent item set by 1. As we said, we extend it by 1 at every iteration. The way we do that is we find all combinations of size k plus 1. K here is 1, so we find all combinations from these items, from the frequent item set, as we said, of size k plus 1. So we want, by the way, regardless of the order. So the order of the items is not important. So we can say 1, 2, or 2 and 1 are the same. So we build 1, 2, 1, 3, 1, 5, 2, 3, 2, 5, and 3, 5, as you can see here. And then what we do is we build the k plus 1 item set, a list of our items, and then we count their appearance now in the original transactional database. The 1 and 2 it only appears once, as you can see there. 1, 3 appears 3 times, 1 there, 1 there, 1 there, and we count the appearance of these item sets, of these combinations in the transaction database. Now, again, minimum support count is 2. Anything less than that should be removed. That's why that one is red, so we remove that, and we end up with the frequent item set in the second iteration looking like this. 1, 3 appears 3 times, 1, 5 appears 2 times, and so on and so forth. Again, nice and easy. Now in the next step, again, we need to extend the size by 1, so we increase k. K here is 2, then k becomes 3, and then we find all possible combinations of size 3 regardless of the order, i.e. the order is not important. What that means is we can have 1, 3, 5, 1, 2, 3, 1, 2, 5, 2, 3, 5, and what else? Yeah, so we'll end up with 4 combinations. Yes? Again, we do the combinations 1, 2, 3, 1, 2, 5, 1, 3, 5, and 2, 3, 5, and now we use the pruning step. What that means is we find all combinations from each item set of these. Now we find all combinations of size k minus 1. You may ask, why didn't we do it here? Because 1, 2, we can break it down to 1 and 2. Well, we've done that in the first step. We've handled 1 and 2 in the first step anyway, so that's why we don't do it there. And here we only break it down to a subset of size k minus 1, i.e. k here is 3, so we only have every subset will be of size 2, 1, 2, and 1, 3. We don't do 1 on its own to its own. Why? Because we've handled these in the first step anyway. So what we do is we break it down to smaller subsets of size k minus 1 again, and we check those now. We check the new subsets in the frequent item set from the previous iteration. Notice, not in the candidate item set, but in the frequent item set from the previous iteration. So let's have a look at those subsets. So for the first item set, we can have 1, 2, 1, 3, 2, 3. For the second one, 1, 2, 1, 5, 2, 5, and so on and so forth. For the 4 of them, for these 4 guys. Yes? Now, we check these, as we mentioned, in the frequent item set. I need to have this in the frequent item set from the previous step. So this, yeah, from the previous step. I hope that makes sense. We check each of these in the frequent item set from the previous step. So 1, 2, is it there? The answer is no. So if any of them, remember, if any of these subsets is not in the frequent item set from the previous step, then we remove that item set. So 1, 2 is not there, immediately remove it. No, that's why it's red, we remove that. 1, 2, 5, 1, 2 is not there, yes, it's not there, so that's why it says no, we remove it. For 1, 3, 5, 1, 3 is there, 1, 5 is there, 3, 5 is there, likewise for 2, 3, 5, all of these combinations, all these subsets are in the frequent item set from the previous step. That's why we keep them. That's how pruning works. Now, after pruning now, we end up with these guys, with these two item sets, and now we count how many times they appear, those combinations appear in the original transactional database. So now we count the support count. 1, 3, 5 appears twice, 1 there, 1 there, 2, 3, 5 also twice, 1 there and 1 there, and those two values are equal the minimum support count, so we keep them. Remember, support count, we said it should be less than the minimum support count rather than less than or equal. After that, now what we want to do, now we increase them by 1, i.e. we find all possible combinations of these items of size 4, because now k is 3 of size k plus 1. So the only combinations, as you can see, we will have in this step now is 1, 2, 3 and 5. If the dataset was larger, then we end up with larger frequent item sets. Then we just try to do the combinations in the same way. I'm just keeping things simple here, but things work in the same way if the database was much larger. Now we build the combination 1, 2, 3 and 5, and then if we try to count the support count, how many times that combination appears in the original database, then it only appears once, i.e. it's less than the minimum support count, so we remove it. We end up with an empty candidate item set in the fourth iteration. What that means is we will have an empty frequent item set, i.e. so we stop there and we return the frequent item set from the first step, i.e. we return this one here. But let's assume that the count was large enough, and then we move on now to the pruning step, i.e. we break that down into smaller subsets of size k minus 1. So k here is 4, we need subsets of k minus 1 size k minus 1, so 3, 1, 2, 3, 1, 2, 5, 1, 3, 5, 2, 3, 5, and then we check these now in the frequent item set from the previous step. Are they there or not? So you can see them here. 1, 2, 3 is not there, so again we remove that anyway, so that will be removed anyway, and we will end up with an empty frequent item set from the fourth iteration, and therefore we stop there and return the frequent item set from the previous iteration, which is 3, the third iteration, and we have now this frequent item set. I hope that makes sense. So now the algorithm stops and returns this list. In the next video, we'll learn now how to use that to extract association rules, which are usually used for maybe recommendation systems and for supermarket layout design or for catalog design and other purposes in general for market basket analysis. Thank you very much for watching.